So now let's get into this Morse potential here. Okay. So the equations that govern molecular vibrations are only approximate, right? That's that rigid rotor model, okay? Or sometimes also called the simple harmonic oscillator model. So the simple harmonic oscillator parabolic motion does not allow for bond dissociation at large displacement, as I showed in the previous slide. So molecular vibrations are what we call anharmonic. So this simple harmonic oscillator model, right, is this perfect parabola. So it's symmetrical. That's what makes it harmonic. Okay? Real molecular vibrations are anharmonic. In other words, they can be broken. They are not symmetrical when we go to higher quantum numbers. And we can see that given here by the Morse potential. Okay? And so here is the equation that governs the Morse potential. And what's important to note here is that dE gives us the depth of the well. So this quantity right here gives us the full depth of the well. All right. And then to actually get the D0, the bond energy, a little bit of algebraic manipulation is done. So we'll say that's dE, and we'll say this one's D0. A little bit of algebraic manipulation is done to go up that level nu equals 0. And that's also based on a few things we know, like the equilibrium bond length and its effective mass. Okay? And so what this also means is generally we always see the fundamental transition in spectroscopy, right? From 0 to 1. Okay? However, in some cases, we might actually be able to skip a level. And so go up 2 levels at a time. And that is due to this anharmonicity. Okay? So that, depending on the strength of the vibration and the width of the well, so as you might imagine, as the well gets wider, right, if you recall this description of the particle in the box model, as the well gets wider, those energy levels are going to get closer together. And so a very, what I'll call a floppy bond, so a not rigid bond, right, can occasionally violate that fundamental transition from 0 to 1. Okay? And so now here you can see I got a whole bunch of equations on here, and I'm not going to spend a whole lot of time discussing these because you're going to dive right into these on your Spec 2 assignment. And so I'll just briefly comment that here you can see up to this point, this is our normal solution to the Schrodinger equation, which assumes harmonic motion. Okay, so this assumes SHO, simple harmonic oscillator. And now we've got this other part on here that describes the anharmonicity. Anharmonicity, yes. So that extra term is given as this extra quantity here with this factor XE. And XE is a ratio of the vibrational energy to the depth of the well. Okay? And so typically what is done in spectroscopy is these quantities are calculated via data fitting. So via curve fitting. We record the spectra and we get those values from fitting the data. And I'm going to describe to you how we do that. In a moment, I'll describe how we do that. We have to first, of course, start thinking about when we would expect to see this anharmonicity. We talked about it with floppy bonds, okay? But also, we can see it when the molecular rotations are coupled with the molecular vibrations,